We have some pretty specific instructions. We're supposed to find an x value, a positive x value that corresponds to a local maximum value of this rational expression composed of cubics. Now, y'all, I was kind of picky about the local here because notice that because we have a cubic denominator, just the standard unshifted cubic function has this sort of behavior, right? So it does have, it's equal to 0 at the origin, and this is just for x cubed, right? Now, any other version of x, any other third degree polynomial is going to look like this as far as in behavior. That means it has to, all cubic polynomials has to have at least one 0, and that means since it's in the denominator, you would be having a division by 0, which corresponds to a vertical asymptote. So you see, vertical asymptotes can go crazy up and down, and they can get larger and larger and larger, or smaller and smaller and smaller, depending on which side you are. So that's why I went ahead and specified local here, just so there wouldn't be any intimation that it was an absolute maximum value. Okay, now let's get busy on this. Now, notice right off that these 4 times these 3 terms, 4 times these 3 terms, x cubed minus 9x squared minus 21x, equals to the 4 terms right above it in the numerator, okay? And also notice that 4 times 5 is 20, and that's where you would get this remainder of 9 here, okay? Again, 4 times 5 is 20. The 29 from 20 leaves you this remainder of 9. So we didn't have to do anything too fancy to produce this remainder of 9 right here, okay? Now, it turns out that's not particularly important that it is 9, but it's a constant remainder nonetheless. All right, now, another key observation here is to note that the local maximum of the entire expression will occur whenever this denominator is minimum, and that's certainly clear. Whenever this denominator is as small as it can be, this particular fraction will be as large as it can be, okay? And the 4 is just a constant. It's always going to be there, all right? Now, so the approach here is just going to be some standard calculus. We'll call the denominator f of x. All right, so f of x equals the denominator term. So again, we'll do the usual, take the derivative and then find out what the critical values are, and then you can use the second derivative to determine if it's a maximum or minimum. Okay, so f prime. And this is slightly easier than trying to do the quotient rule to the whole thing, in my opinion. So we get 3x squared, just a standard, very well-known calculus rule. That's the rule that everybody on the plane seat next to you can remember about calculus. So we got 9x right here, and then we got minus 21, which is the first derivative. Okay, and then let's see, what can we glean from this? This is equal to 3 times, and y'all, I'm going to go ahead and factor this out. That would be 3 times x squared minus, let's just write it down. 3 times x squared. Now let's see here. Did I make a mistake somewhere? No, that should be 18 right there. Sorry. So we have an 18 right here. Okay, 2 times 9 is 18, so this is 18. Okay, so we can factor 3 out of that, and we'll get minus 6x. And then this is minus 7, right? Okay, so that's our first derivative. Now, notice that if we set this equal to 0, f prime equal to 0 to find any horizontal tangent lines, which is where the local mins and maxes would occur, f prime at x equals to 0. Now that would be equal to 3 times. Let's see, does this factor? I hope so. This is equal to 3 times x minus 7 times x plus 1, right? So we get that x equals 7 would be a positive solution satisfying this, all right? Now we want to know, would that correspond to a min or a max, all right? We need it to correspond to a minimum value, all right? If it doesn't, then there wouldn't be an answer to this, okay? So let's see what we got. F double prime. We're aiming for the second derivative test here, folks. So f double prime of x is equal to what? 6x minus 18. Now notice the thing that makes this fly right now is that f double prime at 7 is positive, right? We can see that clearly. Okay, I'm just going to write it down. Did I do everything? Yeah, 6 times 7 is definitely, so this, I'm just going to say this is greater than 0, right? F double prime at 7 is clear because this 6 times 7 is 42, which is bigger than 18, right? Okay. Now, what does that mean, though? Well, the reason why the concavity is important, that would mean locally you had something looking like this. And this would be 7, let's say. This point right here would be 7. And then some unknown y coordinate we could calculate, but there's no need to do that. All right, and so in a neighborhood of 7, the graph is going to be concave up, which means f prime, or excuse me, f at 7. This implies f at 7 is a local min. Local minimum value, abbreviated for minimum. Okay, local min. But that's exactly what we needed here because this key observation, a local maximum of the entire expression is going to occur whenever this denominator cubic has a local minimum value, but that we've shown that that does happen at 7 right here. Okay, f at 7 is a local min by the second derivative test. Okay, so the answer to the question is x equals 7, folks. X equals 7 gets the job done. And some of you may be saying, well, why didn't you just do the quotient rule to begin with? I think you could. I think the algebra is a little uglier, you know, having to, you know, but perhaps it would work out nicely, you know, but I think it's, believe it or not, slightly less work to do it the way I did it. I could be wrong. Again, the long division, you didn't really have to do it because of the construction of these polynomials, one being the first 3 terms of this one, the first three terms of the numerator are 4 times the first 3 terms of the denominator. So you can just see that, and then 4 times 5 is 20, like I said earlier. So this is a 9, which really didn't come into play here. But anyway, that was the way I chose to attack this one. Let me know what you thought.